S47743.
My name is Yiing Yee. My metric number is S48446.
Hi, my name is Ooi Li Sheng and my metric number is S48412.
Hi, I'm Yeoh here from metric number S48450. We'll be doing presentation for coding later on. Thank you.
A very good afternoon to you. My name is Goh Teik Wei. My matrix number is S48013.
This is the coding for the question 1. So we start with the coding, we start with plot. Since we want to plot the graph, so we use the coding with plot. For the question 1, C1, we want to evaluate Bn. To evaluate Bn, we integrate fx, sine, and pi x. Given x boundary 0 to L, where fx equal to x, L equal to k, and equal to 1. We use the coding Bn equal to integrate 2x sine and pi x, where x equal to 0 to 1. This is the Bn. And next, for the question 1C2, we want to find the first 5 coefficients in the series. So we use the sequence Bn, where n equal to 1 to 5. And this is what the output we get.
So for question 1C3, to sum the first 5 terms in the series and plot the graph, we first define the function C, function n with the variable nxt. We use the sum coding where Bn times x sine n pi x times exponent negative n squared times pi squared times t, where n equals to 1 to n. And we come out this is the function of C. Then we will evaluate it with this is the output. Now we will sum the first 5 terms in the series. We use the coding of sum. Then we copy this to here. And where the n equals to 1 to 5, since we are asked to sum the first 5 terms in the series. And then this is the output of our answer. Then we will assign a name to the previous equation, which is this one. We assign to t. And then we will sub the t value into the equation p, where given t equals to 0 to 1 with step size 0.2. So we use t1 equals to sub t equals to 0 into the function p, and then we repeat this step until t equals to 1 with t equals to 0.2, t equals to 0.4, 0.6, 0.8, and 1. And then lastly, we plot the graph for 1C3, where x is equals to 0 to 1. We use the coding of plot all the t1, t2, t3, t4, t5, t6 with x equals to 0 to 1. And then this is our output, the graph. So for question 1C4, we'll first start with plots. Because we want to clear all the previous data, and with plots is because we want to plot a graph. So for the question 4, to worrying care and investigate the behavior through plotting graph. So we will repeat the step of 1C1 until C3. At first we will integrate the Bn, and then this is the Bn value after integrate. and then we change the value of k equals to 1.5. The previous one is the k value is 1, but now we use k equals to 1.5. So we define the c function with the variable n, x, t, and a k. We will use back the formula, and then n equals to 1 to n, and this is the function after defined. And then we will evaluate this function and put the k value equals to 1.5, and then we will get this as our output. So we will use sum coding to sum the first 5 sequence of the series, and then this is the answer. And then we will assign a name to the function, which is a. We assign a, and then we will put t1, t2, t3, t4, t5, t6 again. We sub the t value equals to 0 to 1 with step size of 0.2, and then we will sub t equals to 0, 0.2, 0.4, 0.6, 0.8, and 1 into the a function. And so we plot the graph with t1, t2, t3, t4, t5, t6, where x equals to 0 to 1, and then this is our graph for k equals to 1 when k equals to 1.5. Next, we repeat again the step. This time we use k equals to 0.5. So we repeat again, same with the k equals to 1.5. And here we evaluate the function, c function, we put the k value equals to 0.5. Then this is our output. And then so we sum all the first 5 series, and then we assign a name b to the function, and then we sub the t equals to 0, 0.2, 0.4, 0.6, 0.8, and 1 into the b function. And then we use the same coding for t1, t2, t3, t4, t5, and t6, where x equals to 0 to 1. And then this is our graph for k equals to 0.5. So from the graph where k equals to 0.5 k equals to 1 and k equals to 1.5, we can see that the gradient of graph is increasing when the k value is decreasing. We can see from here. When the k is 1.5, the graph is like this. The gradient is lesser. But when the graph k equals to 0.5, the gradient is here is steeper. Means the gradient value is larger than compared to the k equals to 1.5. So we also can conclude that the gradient of graph will decrease when the k value is increasing, and then it will finally approach the gradient of graph will finally approach to 0 when the k is enough large. We can actually see from here k equals to 1.5 because the graph already almost going to 0. And then this is because the k variable is normally a constant, which is the thermal diffusivity, meaning that the k is controlling the rate of heat diffusivity, is control the rate of change. And so from the graph we can also know that the heat source is around the position x of 0.4 to 0.6. Since that is the local maximum for the graph, from here we can say that we can see from the graph here. For example, at the x-axis 0.4 to 0.6, the y-axis here of the graph is the local maximum of each of the time. So from here you can know that the heat source will be at here 0.4 to 0.6. So when t equals to 0, the heat is the higher compared to other t. When time in t increasing, the residual heat distributed as sine n times pi x and decays as exponent negative n squared times pi squared t. So for x equals to 0 and x equals to 1, the heat is diffused from the heat source, then the heat lost to the surrounding since. Hence the heat cannot be maintained and moves left and right only. From here you can show from the graph, because here previous we said that here is a heat source, so here got the most of the heat at this point, and then at the end of the metal rod at the x position 0 and 1, the y-axis means the heat at the position is 0. So from here we can know that the heat is diffusing out to the surrounding, means the heat lost to the surrounding, so there is no heat at the position x, 0 and 1. We also can know that the change of temperature is proportional to the concavity of temperature, where the y-axis is the temperature of position x in time t. So from here you can know that the change of temperature is proportional to the concavity of temperature. This we can know from the first equation. The heat equation is the heat equation is del u del t equals to k del square u over del x square, meaning that from here we can know it is directly proportional.
Question 1 C5. In here, we need to repeat step question 1 C1 to question 1 C4. Then, we compare the result found in 1 C3, where given a piecewise function fx. Fx equals to x when x is larger than 0, smaller than 0.5. While fx equals to 1 minus x when x is larger than 0.5, smaller than 1. Then, we repeat the step above by integrating bn with x boundary from 0 to 1. So here is the coding. bn equals to integration to fx times sine n by x, where x is equals to 0 to 1. And here is the equation. So, after that, we need to find the first 5 terms. Then, the coding is seq. Then copy this whole thing inside, and with n equals to 1 to 5. Then we will get the first 5 terms. After that, we code that u equals to, in terms of n x dk, with the summation bn times sine n by x times exponent negative n square pi square kt, with the n equals to 1 to n. So here is the summation equation. So now we sub k equals to 1 inside this equation, we'll get this. After this, we need to sum the first 5 terms of this summation. So the coding is as sum, and copy this whole thing inside this bracket, and then with the n equals to 1 to 5. Then this is the first 5 summation of first 5 terms. Then we name this whole thing as u. After that, we need to substitute t equals to 0 until t equals to 1 with the size of 0.2. So t1 we sub t equals to 0, t2 we sub t equals to 0.2, T3 we sub t equals to 0.4, T4 we sub t equals to 0.6, T5 we sub t equals to 0.8, T6 we sub t equals to 1. Then we will get the graph like this. This is the graph for k equals to 1. So after this, we repeat just the code just now. We have key in. Just the difference is k. This time we substitute k equals to 0.5. Then again, after we get this equation, we sum the first 5 terms. So we'll get this. This is the first 5 term of n with the k equals to 0.5. So we name this summation as A. So at here it's the same. It's the same. We sub t equals to 0 until t equals to 1 with the size of 0.2. Then this is the graph for k equals to 0.5. So again, we repeat the step above again. All the things is the same as above. The only difference is k. This time we sub k equals to 1.5. So after sub k inside, we will get this summation equation. Then we sum the first 5 terms. We will get this first 5 terms. We name it as B. Again, we need to substitute t equals to 0 until t equals to 1 with the size of 0.2. Then we will get this graph. This graph is where k equals to 1.5. So from the graph we have plot above, when fx equal to x, the graph for both when t equals to 0 have the highest heat. However, the heat diffusion is different for both at t equals to 0. For first graph, fx equals to x, the heat flow is randomly, while the second graph with the piecewise function, the graph gradient is following the fx equal to x, which is increasing, and x is larger than 0.5, the graph gradient is following fx equals to 1 minus x, which is decreasing. Both graphs having the same experience. When time t is increasing, the heat will decrease. This is because they have the same constant k, which is thermal diffusivity k equals to 1. So in conclusion, when time t increasing, the residual heat distribute will decay by losing to surrounding. When the temperature of the metal rod will decreasing by time increasing. Question 2b part 1. In here we need to evaluate Bn. So here is the code. Here is the coding. Bn equals to integration 2 times x times sine n by x, where x is equals to 0 to 1. Then we'll get this equation.
Hello, I'll be doing explanation for 2b, part 2 and part 3. For formula 2, I will find this term, first term to the fifth term by the sequence of the formula given. That's how we get part 2. So for part 3, formula 3, we will let Bn be 2 integrate x sine 2n minus 1 by x over 2 from x equal to 0 to 1. That's how we get formula 3. For formula 4, we will evaluate formula 3. That's how we get the formula 4. So for number 5, we will assign the Bn value into the general formula uxt. That's how we get formula 5. Okay. And to get formula 6, we will evaluate the whole formula 5. Okay. And then for formula 7 found is the summation of the whole uxt from n equal to 1 to 5. Okay. Finally, is like to get formula 8, we will evaluate the whole formula 7. Okay. Then for 9, we will assign the coefficient of 8 BU. Okay. Then we assign the value t equals 0, 0.2, 0.4, 0.6, 0.8 to 1.0. And the answer will be represented by answer 1, 2, 3, answer 4, answer 5, and answer 6. So that's how we get under formula 23. For formula 21, we will plot the answer found, and from x equal to 1, x equals 0 to 1. Okay, so this is the graph found. That's all. Thank you.
Hi, good afternoon. Today, I will explain my coding for the question 2. So let's read the question. For the question 2, suppose that at x equals to 0, the boundary condition does not change. However, at x equals to L, the bar is insulated. For example, Ux or Lt equals to 0. Okay, so for my part, I will explain about the B part. The B part of 4 and 5, right? Let me check about it. Yes, 4 and 5. So for the B part, they asked me to repeat the problem in case 1C. Okay, case 1C is by varying K, investigate the behavior of the metal bar temperature through the plot of Uxt for x from 0 to L. Discuss your finding. Okay, for this one, my coding is like this. So, the varying of K, we have to change the K value from 1 to any value you would like to change. But for us, we will change to 0.5 and 1.5. Okay, let me explain you for my code. So for the first part of my code, I would like to put the integration of this equation. Okay, after integrate this equation, I will get this answer. This is my answer after I evaluate about this. So I assign another thing which is named as U as summation of the Bn times exponent. Yeah, this is the key point. For the exponent is where we change the K value. The K value is in, let me show you the previous general solution for the, let me find about it. Yes, this is the one. This is the one which is the general one with substitute of K equals to 1. So by doing this, we are doing it K equals to 0.5. So it will become 1 over 8 times 2n minus 1 square times pi square times t. Yes, this is the only changes that we change to whole summation of the equation. So after that, we'll evaluate this equation. After evaluate this equation, we will get this. This is the meaning of summation of this whole equation. Of the whole equation, I type summation bracket the whole equation to the n from 1 to 5. So I'll get this. After I get this, I want the number to look nicer. So I type EVALF bracket percentage. So I'll get this. After I getting this, I assign this set of value as U2. For U2, Now I have this set of values, so I can start to substitute my t value from 0 to 1, as the question mentioned, as step of 0.2. Yeah, 0.2. After 0.2, first one, we will substitute t equals to 0 in order for u2. So get this set of value. So we assign this set of value as answer to 1. Okay? Then we will do all this by adding 0.2, 0.2, 0.2, 0.2 until it becomes 1 to get every set of value, which is total 6 set of value. Okay? Repeating the same step. Okay, this is the final one. We have to plot a graph with this 6 set of value. Ta-da! This is the set of value from which plotting a graph, the result we have get. Okay, from this graph, what can I understand from this graph? Okay, from this graph, from point of my view, from what I understand, I would say that all the value is start from 0, and the y-axis is the temperature of the direction of the temperature come in. Why it will start with 0 is because I would say that they start the point at the insulator, so the temperature will be 0, and also from the starting point of time of 0, which is also 0. For the first bar, we substitute t equals to 0. We will get in higher heat of the graph. Then correspondingly, we will get lower, 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 and lower until to the 1. Yeah, this is from what I understand lah. Okay, for next one, I will do for the k equals to 1.5. As same as the first one that I say k equals to 0.5. I doing all of this, all of the step, all over again to get all these values, all of the same step, and plot the graph. We will get this graph. Okay, this graph is slightly different from this graph. Do you see any difference? I guess you see it. Yes, the first graph, the first line, the red line of the graph has no changes. It's because when t is substituted to the same equation, it will be 0. 0 to the anything is 1. Power 0 to the e is exactly the same answer as anything you substitute to 0. Okay. Second line we substitute as 0.2 for the time. Okay, 0.2. Yeah. When k is equal to 0.5 and k is equal to 1.5, the transfer heat applied, which is lower, will make the graph go even higher. So, as me explained in the explanation part, we can see that from the graph, k equals to 0.5, k equals to 1, k is equals to 1.5. We can see that the graph of the gradient of the graph is increasing when k value is increasing, while the gradient of the graph is decreasing, when k value is increasing. And finally, it will approach to 0. Maybe not 0, maybe eventually it will approach to 0 when k value is large enough. This is because the k variable is normally constant, which is thermal diffusivity. We're controlling the rate of heat diffusivity when T increasing. Yeah, this is because when some heat is applied to the line, when K value is getting larger and larger and larger, the graph will getting curve and eventually curve until go to the end, means 0. I guess won't go to 0 because we don't really know it have insulator or not, but as we know, from x equals to 0 and x equals to 1, the heat is hardly diffused from the heat source. Then the heat loss to the surrounding is less, since there's insulator covering the metal rod. Hence, the heat can be maintained and moved left-right. We can also know that the changes of the temperature is proportional to the concavity of temperature, where the y-axis is the temperature of position x in time t. Also, from the graph we have plot above. Okay, so that's it for my question 2b for part 4. Thank you. Hi, good afternoon. Now I'm going to talk about another part of my question, which is the C part of the 5, which is repeat C1 to C4 and compare result to those found in, I think this is a wrong question for where this is a, okay, let's ignore about this, okay? So what they want us to repeat is to use this piecewise function to apply into the coding that we have used just now. Okay, so let's start. So I assign fx to the piecewise 0 less than x, 0, x less than 0.5, and the equation is x, and another one range is 0.5 to 1, and the equation is 1 minus x. After I evaluate, I got this, and then we use the equation that we have integrated above, which is blah blah blah, this, then we get this. After we evaluate this, we get this set of value. So we have to repeat every single thing in part 1 to part 4. So part 1 is about to evaluate the equation, which is this. Part 2 is about this, the sequence. The sequence is, first one is this, second one, third one, fourth one, and fifth. And the third part is the one we're doing just now, which I use this equation for doing all that and substitute all the things into the equation and get this. Okay, for the first one, I substitute k equals to 1 to my solution, which is we'll get this set of summation of value. So I type summation to this value, and n is equal to 1 to 5. Then we will get this set of value. So we assign this set of value into u. the function u. So as we substitute the t value is equal to 0, we'll get this value, this set of value. And then we subs 0.2 into this value, we'll get this value. And correspondingly, we'll get all 6 values and plot into a graph, which is look like this. Okay, from my point of view, why my graph will look like this? Let me tell you. For the first one, the first set of value, I'll get barely like a bell shape. The bell shape, which means that when the heat goes from 0 or maybe near to 0 up to the highest peak, and after it cools down, it goes to the normal temperature, right? And then for the other graph, it didn't goes to very low for to the 0, because it don't have enough big of k value, so it will not show the whole graph. It's supposedly be like this, but the k value is small enough, so we won't get the whole value for the k. Okay, let's repeat with another set of value. So let's just skip this because it's the same as the entire thing. So we'll skip to the third part, which I sub k value equals to 0.5. I'll get this summation blah blah blah, get this, and assign as u, substitute 0 until to 1, then we plot a graph. Boom, we get another graph of this. So did you see any difference from the graph? I would say that the graph barely moved upward. Why it will move upward when the k value is getting smaller and smaller? As the same theory as the part 4 that we said just now. The higher the k value, the lower the gradient. The lower the k value, the higher the gradient. Okay. For next one, we'll substitute for 1.5. We'll skip all this. 1.5. And summation of this, blah, blah, blah. Get this. And assign as u again. And then t1, blah, 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 under the 1. Okay. Now, the graph is getting lower and lower when your t value is equal to 1.5. 1.5. You see that? The k value is getting lower, higher and higher, and your graph is getting lower and lower until it will touches the x-axis to the same graph. So from the graph, we have plot above. When fx goes to x, the graph for both when t equals to 0 have the highest heat. Both graphs having the same experience. When time is increasing, the heat will decrease. This is because they have the same constant of k, which is the thermal diffusivity is k equals to 1. So let me explain to you. So that we can just conclude that when time t increasing, the residual heat distributed will decay by losing to surrounding. Hence, the temperature of the metal rod will decrease by the time increasing. Thank you for watching. Bye.